Welcome. Let's take a look at our last review session together this year. Semester 2 review does cover chapters 5, 6, 7, and 8, so 4 chapters. The review notes that I put together along with this video don't include chapter 8, since we just finished that in week 37 with a review and a test. So there is no chapter 8 on this review. You will see it on your homework, though. Your homework is about, I think, 40 questions. Here, actually, take that back, 30 questions. Your test is about 15. So anything on that test is going to come from the review. We didn't cover it in the review. You don't have to worry about it being on the test. I didn't include things like trig identities, since we spent so much time on those with the partner projects, the worksheets, the assignments at the time. So we kind of exhausted that. I'm not going to hit those again. It's going to be a lot more of just the straightforward, quick processes to review and refresh those basics behind. Chapter 5 looked at things like inverse functions and logarithmic functions, and then 6, 7 and 8 were your trig functions. So a little more basic than what we really dug into when we were looking at. So let's go ahead and get started. Our first question here, we're looking at composite functions, and we're given 2 functions, f of x and g of x, and we're asked to find 4 different values here. So remember, with composite functions, the big thing is that we work inside out. So for part A here, we want to find f of g of 4. So start by finding g of 4 and put that output in for the x component of your f function once we get there. So let's go g of 4. That's like taking 4 times 4 squared plus 5, and 4 times 4 squared plus 5 is 69. Now take that output of 69 and plug that into your f function. And f of 69 is 9 times 69, which is 621. So your final solution for part A is 621. Part B wants us to find g of f of 2. So again, start with your inside. Start with f of 2. 9 times 2 is 18. And take that output of 18 and plug it into your second function. G of 18 says 4 times 18 squared plus 5. 4 times 18 squared plus 5 is 1,301. Now the next two look a little bit different. I want to find f of 1. Similar process. Still start with the inside, which I guess the inside and outside are both f. So f of 1, 9 times 1 is 9. Now take that output and plug it into your second function, which again is f. Now f of 9 is 9 times 9, or 81. And lastly, very, very similar, just using g of 0. So start with g of 0, 4 times 0 squared plus 5. Only thing times 0 is 0, but we have plus 5, so we do get 5 as my output. And then finish it with g of 5. 4 times 5 squared plus 5. And that gives us 105. So just a quick review on composite functions. You do have a couple questions in your homework where you'll also be reviewing composite functions with graphs and working inverse functions as well with graphs. So just kind of keep that in mind. Speaking of inverse, let's go ahead and do an inverse here. We have this function f of x equals x squared minus 6, where x is only positive or equal to 0. So x is greater than or equal to 0. And we're told it's 1 to 1. We want to find the inverse. Remember, it has to be a 1 to 1 to have an inverse. So to find our inverse, switch the y and the x. So think of f of x as y and then switch them. So x equals y squared minus 6. To find the inverse, solve for y. I'm going to start by adding 6 to both sides. X plus 6 equals y squared. And to get that y by itself, we're going to square root both sides. Now, hopefully this is maybe ringing some bells for you, and you're thinking, hey, when we take the square root, we should be taking the positive and negative. But notice, we're told to restrict that domain to positive x values. So we don't have to worry about negative. That's what makes this a function instead of being a positive and negative, which would give us not a function. Also know how to graph that. You'll see that in your homework as well. All right, moving along, the rest of chapter 5, we looked at exponential functions and logarithmic functions. As a reminder, by definition, a function is an exponential function if x is in the exponent. So if x has a power, that's a polynomial, like x cubed or 5x squared. If x is in the exponent, like we see here, 4 to the 2x plus 1, this is an exponential function. So be aware of the differences there. Now we have a couple approaches. Before we really learn how to solve any exponential function, we talked about some tips and tricks that will make it quicker if we can do. So I want you to know, you can solve any exponential function by taking the log of both sides and solving for your variable. We're going to do that a little bit later. But before we do that step, because that step can be kind of nasty, we use a lot of logs or natural logs, and we can have a lot of rounding and ugly answers. We always want to see if there's a shortcut. In this case, if I can get my base on either side to be the same, then if my bases are the same, that means my exponents are the same. So I'm going to rewrite my left-hand side. I'm going to leave that as 4 to the 2x plus 1. And I'm going to ask myself, can I rewrite 16 as a value that has a base of 4? So is there any number that I could rewrite this 4 to some power that would give me 16? And the answer is yes. 4 squared is 16. Now, if you look at your function, 4 to the and 4 to the means that whatever those exponents are has to be the same. If your bases are the same, your exponents are the same. So now I'm just left with 2x plus 1 equals 2, and there's a two-step equation. Subtract 1 from both sides, so 2x equals 1. Divide both sides by 2, and x is 1/2. So we could have solved this using logs and we would have got the same thing, but it just would have been a longer, kind of nastier process. If you can rewrite it so your bases are the same, it's going to save you some time. All right, changing back and forth between exponential functions and logarithm functions. The key to remember here is that your base stays the base. Okay, so here, if you want to read it this way, e to the x equals 18. E is my base, x is my exponent, and 18 is my argument, is the word they use sometimes. So my base stays the base. So log of e, then your other two values switch. Log base e of 18 equals x. And you can do that anytime. Any exponential function can be rewritten in logs this way. Now, in this special case, we actually aren't done here. Most of the time you would be. But we do have this special case, or this special term for what we call log base e. And that's our natural log that we shorten to ln. So instead of writing log base e, we're just going to write natural log of 18 equals x. And that's going to be the most simplified. So anytime you've got log base e, we want to simplify that to be natural log. And this is that look at, we're going to take a look at this one where we're solving another log function. And again, we're going to use a shortcut first before we go ahead and use the method that would work every time, which would be to raise everything to be an exponent. So in this case, what I'm going to do is I'm actually just going to take the function as is, log base 2 of 7x plus 6 equals 6, and I'm going to rewrite the log function as an exponential function. So that last one, we did the opposite. We did an exponential function as a log. Now we're going to work the other way around. So this is log base 2. Base stays the base, switch the other two around. 2 to the power of 6 equals 7x plus 6. Well, 2 to the power of 6 is just a number, that's 64. And again, with just one step there, I now have a two-step equation that I know how to solve. So if you can simplify it by just rewriting it in terms of an exponential function, do that and save yourself some time. Subtract 6 from both sides, 58 equals 7x, divide both sides by 7, and x equals 58 sevenths. Okay? And our last Chapter 5 review here is working with rewriting or using exponential functions and solving them using logs. So I've got 5 to the x equals 9. Now remember, the last time we tried solving an exponential function, we asked ourselves, could we rewrite the other side to have the same base? Well, there is no way I can take 5 and have an exponent that's going to give me 9. So 5 to no power gives me 9. So I can't use that method. So instead I'm going to use the log method. Now I'm going to use log, and I'm not going to write a base. Just as a reminder, that means it's an implied base 10. That's something that our calculator can do. If you prefer, you could use natural log, or you could use any base you want, although most calculators don't do it in any other base, so it's going to save us time by putting it into log base 10. So I'm going to start by taking the log of both sides. Log of 5 to the x equals log of 9. Just like with our algebra steps, as long as you do it to both sides, you're still creating an equal equation. Now I need to get rid of this x and the exponent. And once we have logs, remember, if there's an exponent of what you're taking the log of, you can actually move that to the front of the equation. So this becomes x times log of 5 equals log of 9. Now, log of 5 and log of 9, those are just numbers. They're probably not very nice numbers. They're irrational, but they're still numbers. So if I want to get x by itself, I just need to divide both sides by log of 10. Oops, log of 5, excuse me. So when you hit this one in your homework, it's going to ask for two answers. The first thing it's going to say is, give me an exact answer. The exact answer is that x is equal to log of 9 divided by log of 5. And as I mentioned, if you prefer, you could replace all of those log-based 10s with natural log. It would still give you the same answer. It's also going to ask for an estimated answer. And for that, you'll need your calculator. And the big thing here is when we take log of 9, just make sure you close that parenthesis before you do divided by log of 5. And we get about 1.37. So an exact answer is leaving it in terms of log. A rounded answer, just put it into your calculator. If you have any other questions over the Chapter 5 review that's included in the homework assignment, shoot me an email. I'd be happy to go over those with you. Now, as I mentioned, for Chapter 6 and 7, I kept it pretty basic. There's not going to be a lot of really involved problems, just a big overview of those topics that we covered. So I do have a few where we're going to practice just using our calculator. And the reason that I included this in here is that after doing Chapter 8, I'm guessing that your calculator is in back in degrees. We need to make sure that our calculator is in radians when we want to find exact values using our, approximated values using our calculator. So as a reminder, if you're using your graphing calculator, oops, wrong button, we go to mode up here at the top next to the second button and arrow down, make sure that you have radians highlighted and not degrees. And that could be a very tricky situation for you because for your semester final, you will need to be converting back and forth. Your questions will go in order, so you'll want it in radians for the first portion and finish it with degrees for your Chapter 8 questions. Be conscientious of that. Don't lose points because of your calculator. And remember, we don't have a cotangent button on our calculator, so we have to find this taking 1 divided by tangent of pi over 13. And that's the way our calculator can do a cotangent, using that reciprocal function. So 1 divided by tangent of pi over 13. And let's just round to 2 decimal places. We get about 4.06. So here I'm just really concerned with making sure that you get your calculator in the right mode. All right, next looking, Chapter 6, we talked a lot about finding all of the trig functions if we know just a few of the trig functions. So if I know that sine of theta equals negative 5/13, and theta is restricted between 180 and 270 degrees, what are the other 5 functions? So for this, we're going to need to figure out what quadrant we're in. Between 180 and 270 means we're in quadrant 3. And we're going to draw ourselves just a little bit of a sketch graph here. And I don't care if it looks like it's about accurate. Just make sure it's in the right quadrant. And try that again. There we go. Since sine is equal to negative 5/13 and sine is y over r, I know my y value has to be negative 5 and r is 13. Remember, r, or your radius, your hypotenuse, will always be positive. X and y will be positive or negative depending on the quadrant. So before I even go any further, I do notice that I'm in quadrant 3, which means my x value will also be negative. And to find that, I'm going to use Pythagorean theorem. So 13 squared minus 5 squared gives me 12. So now I have an x value of negative 12. I kind of grouped some steps together there. If you need to work the Pythagorean theorem step by step, by all means go for it. You can pause the video and go ahead and work that out and make sure you get the same thing I do. Then find your trig functions. Cosine of theta is x over r, so negative 12 over 13. Tangent of theta is y over x, negative 5 over negative 12. Negative divided by negative is positive, so 5/12. Cosecant of theta is the reciprocal of sine, so negative 13 over 5. Secant of theta is the reciprocal of cosine, so negative 13 over 12. And last, we've got cotangent, which is the reciprocal of tangent, so 12/5. Be familiar with that. You have a few of those to varying degrees. Some of them, they give you 2. You've got to find the other 4. Others like this, you have to plot your point, figure out your quadrant, and use Pythagorean theorem. But we did a lot of that, so hopefully that's fairly review for you and not too troubling. Here we just want to find our exact values. This is just, can you read that unit circle, or do you need a refresher on how to do so? So the first one asks us to find tangent at pi over 4, and I've got my unit circle right here. Pi over 4 is the point root 2 over root 2 over 2 and root 2 over 2. And tangent is y over x, or sine over cosine, either way you want to think of it. So square root of 2 over square root of 2 over 2, anything divided by itself is just 1. So tangent of pi over 4 is 1. Part B asks us for sine of pi over 3. Again, if you need to, if you don't have this memorized, that's okay. Pull up your unit circle. Pi over 3 is a 60-degree markup here in quadrant 1. Sine is our y value, so sine of pi over 3 is root 3 over 2. So not a whole lot of extensive work there, just making sure you're familiar with the unit circle and can read that still. The next two work with finding values, solving. Actually, the next three, we're going to kind of have a solving process going on here. So here's a composite function with trig. So it's kind of like mixing what we did in the very beginning with what we did with our trig functions. Same rule applies, work from the inside out. So I'm going to ignore the cosine right now, and I'm just going to work on solving what inverse sine of negative root 3 over 2 is. And remember we said when we're working with inverse trig functions, go ahead and set it equal to theta, and then rewrite it so it's no longer inverse by switching your values. Sine of theta equals negative root 3 over 2. So what we're saying here is that what angle do we have when our sine value is negative root 3 over 2? Or what is the radian value when the y value is negative root 3 over 2? Let's look at our unit circle. So we want a sine value or a y value of negative root 3 over 2. Notice that happens here at 4 pi over 3, and that happens here at 5 pi over 3. Now, when we're working with inverse functions, remember in order to get an inverse, we have to have a one-to-one function. And sine itself is not one-to-one. None of our trig functions are itself. So, well, I should say it. But we restrict our inverse function to be in, for sine, quadrants 1 and 4. So even though I do have a negative root 3 over 2 at 4 pi over 3, that's not in my domain for my inverse sine function. Only quadrant 1 and 4 are, so I'm going to use 5 pi over 3 here. So theta is equal to 5 pi over 3. Now that means that I'm going to replace all of this with 5 pi over 3. And that gives me the function, what is cosine at 5 pi over 3? We'll go right back to that unit circle. 5 pi over 3 is this location right here. Cosine is the x value, which is positive 1/2. So my final answer here is 1/2. Working from the inside out. All right, here next one we're actually solving because we have an equation set equal to 0. We have 2 sine squared theta minus sine theta equals 0. And what I noticed first right away here is that I have a sign in both of my terms here on the left. So just like if this was an x, 2x squared minus x equals 0, we'd factor the x out and solve by factoring. Here I'm going to factor the sine out. So I factor out a sine of theta. My first term I've got left 2 sine theta. And my second term I just have minus 1. And set that equal to 0. Now we're going to use the zero product property. Set each of those equal to 0. And solve for theta. Sine theta equals 0. 2 sine theta minus 1 equals 0. And solve. Where on my unit circle is sine or y equal to 0? That happens at 0 and pi. Over here, I'm going to add 1 to both sides and divide both sides by 2, which gives me sine theta equal to 1/2. So again, if you need to, go ahead and reference your unit circle. Where is y positive 1/2? Well, right here at pi over 6 and over here at 5 pi over 6. So theta is also equal to pi over 6 and 5 pi over 6. So I do have 4 answers here. That's okay, that happens. Just include all 4 in your solution. All right, and our last one, the only kind of extensive identity that you're going to have to review is the sum or difference identity. That's what we're going to do here. Don't worry about your double angles, your half angles. We're not going to hit that in our semester review. So here we're asked to use a sum or difference formula to find the exact value of this trig function. We want to know what sine of 5 pi over 12 is. Well, we can't put it in our calculator because that doesn't give us exact values. And we can't use our unit circle because 5 pi over 12 isn't on my unit circle. So I need to rewrite this in terms of values that are on my unit circle so I can solve. So you could do this a multitude of ways. As long as the values you split 5 pi over 12 into are values in the unit circle. So I'm going to say, hey, 5 pi over 12 is the same thing as 3 pi over 12 plus 2 pi over 12. You could use this as a difference formula. Just make sure that you use the right formula then when you're converting. And now if I simplify, 3 pi over 12 is pi over 4 plus 2 pi over 12 is pi over 6. Notice now I've got two values that are on the unit circle. But remember, I do not just take sine of pi over 4 and add it to sine of pi over 6. I need to use my sine sum formula, which says sine of my first value, or like alpha, pi over 4, times cosine of beta, which is pi over 6, plus cosine alpha, cosine of pi over 4, times sine of beta, sine of pi over 6. Now I can do a direct substitution. What is sine at pi over 4? That's root 2 over 2. What is cosine at pi over 6? That's root 3 over 2. Plus, what is cosine at pi over 4? Root 2 over 2. And sine at pi over 6 is 1/2. I'm going to start by multiplying my first two terms together. Square root of 2 times square root of 2 is square root of 6. 2 times 2 is 4. Plus, square root of 2 times 1 is just 1. Or excuse me, just square root of 2. And same denominator here, 2 times 2 is 4. So final answer, add across the top, and your denominator stays the same. Square root of 6 plus square root of 2 all over 4. And you may see it written like this, so you pull the 1/4 out front instead of dividing the whole thing. It doesn't matter. Both are correct. So remember, Chapter 8 is also on your review. I just didn't include it here since we just did that in class. But feel free to take some time to review that, ask any questions that you have. And good luck on your test. As soon as you're done with the chapter test or the semester test, you are done in this class. Let me know if you have any questions.